Welcome back to the Deep Dive, the show where we really try to cut through the noise and get straight to those aha moments in cutting-edge research. For many of us, the phrase large language models or LLMs, well, it immediately brings to mind these incredible capabilities, right? Generating code, writing essays, even tackling complex math problems. But behind that magic, there's this whole world of intricate training techniques. And maybe none is quite as buzzing right now. None feels like such a frontier as reinforcement learning, or RL for LLMs. So today we're diving deep into a really fascinating and I think quite clarifying new paper from ArcSenf. It's called Tricks or Traps, a deep dive into RL for LLM reasoning. And this isn't just, another paper adding to the stack. It's really a critical look, trying to bring some much needed clarity to a field that's evolving super fast and maybe frankly, is a bit chaotic right now. We're talking about making sense of hundreds of new techniques popping up, figuring out what actually works, and crucially, why it works.
Exactly. The research community has seen this explosion of RL for LLM or RL for LLM studies. It's everywhere. But, with this rapid progress, we've also seen significant fragmentation. It's a real issue. You get contradictory findings, inconsistent experimental setups, a real lack of clear, consolidated guidelines that leaves practitioners navigating what feels like a maze. So our mission today is to unpack this paper's systematic review. They looked really rigorously at widely adopted RL techniques. We'll analyze their internal mechanisms, try to understand their applicable scenarios, and highlight the core principles that truly drive performance. Our focus, as always, will be on the technical details and implications. We'll be skipping over any ethical or inclusivity considerations as the paper doesn't focus on these. And of course, for those looking to stay updated on the latest AI and ML research papers, remember to visit neural-intel.org and check us out on YouTube.
Okay, so zooming out a bit, what's the big picture problem this paper is trying to solve? It really does feel like the Wild West of RL4 LLM, right? Everyone's got a new trick, but nobody's quite sure if it's genuinely helpful or just, the hidden trap waiting to mess things up.
You've absolutely hit the nail on the head. Imagine having this massive toolbox, hundreds of tools, but no instruction manual. And half the tools seem to contradict each other for the same job. That's pretty much the scenario this paper tackles. For instance, some really influential research advocates for group-level normalization for policy stability. But then others argue quite strongly that batch-level normalization is actually superior. And then one study even recommends removing variance normalization altogether to prevent certain biases, which directly conflicts with others who say it's essential. So this proliferation, combined with different models, different data, it just creates huge barriers for practical adoption. This work is really about demystifying all that complexity, helping people understand when and why to use specific methods.
Okay, let's unpack this then. So for someone actually building or trying to improve an LLM with RL, the key questions are, which techniques work for which situations? And maybe, is there a simpler, more general combo that actually works reliably, like a baseline that's solid? That's the practical compass we need, I think. Okay, so the paper makes this strong case that RL has become a key driver for advanced reasoning in LLMs, especially for tough stuff like math and code generation. But why is RL so fundamental here? What does it actually do that the massive pre-training alone can't quite manage?
That's a really foundational question. And what's fascinating is how RL elevates LLMs beyond just, static knowledge learned during pre-training. Think of pre-training like giving the LLM its huge vocabulary, its grammar, its general understanding of the world and language. It learns to predict the next word incredibly well. But for complex reasoning, tasks needing multiple steps, maybe self-correction or sticking to very specific formats, pre-training often falls a bit short. It can generate text that looks plausible, sure, but not necessarily text that's correct or follows the optimal reasoning path. And that's where RL comes in. It allows for this dynamic fine-tuning process. It explicitly optimizes for these desired behaviors. So instead of just predicting the next token, the model takes actions-generating tokens and gets a reward signal based on the quality of its whole output. Did it solve the math problem correctly? Is the generated code valid and efficient? This feedback loop lets the model learn not just what to say, but how to achieve a specific goal. It's about shaping the model's behavior towards an objective. That's a big leap beyond just pattern matching in text. This explicit, dynamic optimization is what gives it that extra edge for genuine problem solving.
Right, so if pre-training teaches a chess player the rules, RL teaches them the winning strategies, how to actually play well. But then, as you said, we hit this problem of too many strategies, too many conflicting approaches in the research.
That describes it perfectly. Yeah, the rapid surge in research, while exciting, has definitely led to a fragmented understanding. It's a real labyrinth, like I said, a toolbox full of unlabeled, contradictory tools. And this isn't just academic disagreement. It causes real confusion and wasted effort for practitioners trying to apply these techniques. Let's get specific about that fragmentation again. Take normalization. GRPO says use group level. Reinforce plus says batch level is better. Then Dr. GRPO says maybe remove variance normalization entirely, directly contradicting others. Or loss calculation. GRPO found success with response level loss, focusing on the whole output. But DPO uses token level loss, weighting each token. These aren't minor tweaks, right? They're fundamental choices in how you build the RL algorithm.
Yeah, those sound like choices that could completely change how the model learns. So why do these conflicts, these disagreements even happen?
The paper points squarely at inconsistent experimental settings across different studies. It's a major culprit. Think about it. If you have variations in training data, different model initializations, different model sizes, different architectures, each of these can mess with the results. So if one paper tests technique A on a 7 billion parameter model with dataset X, and another tests a variation on a 13 billion model with dataset Y, well, it's really hard to isolate the true effect of technique A itself. You've got all these confounding factors. It's hard to know if a technique is genuinely better or if it just looked better because of the specific setup it was tested in. Without a unified framework, a controlled environment, it's tough to compare apples to apples. This lack of comparability really hinders progress.
Okay, and this is exactly where this paper, this deep dive comes in. The researchers basically said, okay, let's control for all that. They systematically reproduced and evaluated these techniques in a unified open source framework using the same models. That sounds absolutely crucial.
It is, and it represents a huge amount of careful work. By controlling variables like dataset difficulty, model size, specifically Quen34B and Quen38B, both base and aligned versions and model types, they could do what they call a fine-grained analysis. This rigorous approach is designed to reveal the true preferences and sensitivities of each RL technique. By stripping away those confounding factors from different setups, they provide solid empirical evidence that can actually guide practitioners on when and where to apply these techniques effectively. It's about moving from scattered results to a more scientific, reproducible understanding. That's what really pushes the field forward.
All right, before we get into the weeds of all the individual tricks and potential traps, let's establish a baseline. PPO, proximal policy optimization. That's often seen as the workhorse, right? And the go-to for many RL tasks. What's its core idea?
PPO is definitely a cornerstone, widely used because it hits a sweet spot between performance, stability, and relative simplicity. At its core, it's an actor-critic algorithm. So it learns two things at once. An actor network decides what actions to take, in our case, which tokens to generate. And a critic network estimates how good those actions are, predicting the value of a state. The main idea in PPO is to improve the policy, the actor's behavior, but in small, controlled steps. It uses this clipped surrogate objective function. This objective encourages the policy to take good actions, ones with high advantage, meaning they lead to better outcomes than expected. But crucially for stability, it restricts how much the new policy can change from the old one in a single update. This clipping hyperparameter, often called epsilon, is key. It prevents really aggressive updates that could destabilize everything. It keeps the learning incremental and cautious, like having guardrails on a racetrack while you're learning to drive faster, right?
Exactly, like guardrails, making sure the model doesn't just fly off the track during training. Makes sense.
Okay, so now GRPO, Group Relative Policy Optimization. This one takes a different path quite cleverly by simplifying things. It actually gets rid of the critic, that value function. Instead, GRPO estimates the advantage by normalizing rewards within a group of responses generated for the exact same prompt. Imagine grading multiple student essays on the same topic. Instead of absolute scores, you look at how each essay compares to the others in that specific group. You focus on the relative differences. Technically, for a prompt generating G responses with rewards, the group normalized advantage AIT for response I is RI, STD. Basically, how much better or worse was this response compared to the average response for this specific question scaled by the variation? This emphasizes the differences among the candidates for that one prompt. It's a smart form of reward shaping. It helps maintain a clear gradient signal even when rewards are sparse, like just 0 or 1. And instead of adding a KL penalty to the reward, GRPO adds the KL divergence between the trained policy and a reference policy directly to the loss function. It aims for efficiency and stability through this relative comparison and regularization.
That's a really neat trick, getting around needing a critic, focusing purely on relative performance within that group. But what are the potential downsides of not having that critic? Does the paper hint at any other challenges this might introduce? Maybe the model doesn't get a good sense of the absolute value of its actions.
That's an excellent question, and it touches on a potential trade-off. While simplifying the architecture is appealing, a critic-free approach like GRPO might put more pressure on the reward design itself. Without a separate value function estimating the overall goodness of a state, the policy has to learn both what to do and how good it is just from those normalized rewards. So if the group-level normalization isn't perfectly aligned with the true global goal, or if the responses in a group happen to be skewed, well, the model could potentially be more susceptible to reward hacking or misspecification. It might optimize for doing better than its peers on this specific prompt, rather than learning the absolute best strategy overall. So yes, it's a simplification, but one that makes the reward function design even more critical.
Interesting trade-off. Okay, and then there's DAPO, decoupled clip, and dynamic sampling policy optimization. That name alone suggests it's tailored for LLM reasoning challenges. What's special here?
TAPO is definitely geared towards LLMs. It introduces several techniques trying to address specific pain points in LLM reasoning. A key feature is decoupled clipping. It refines the PPO clipping. Instead of the usual symmetric 1ln epsilon, DAPO uses independent bounds, epsilon low and epsilon high. This allows asymmetric treatment. Maybe you want to encourage big positive changes more than you penalize negative ones to help exploration, especially for those low probability but potentially useful tokens. DAPO also does dynamic filtering. It tries to filter out uninformative samples. Like if all responses to a prompt are correct or all are wrong, there's maybe not much to learn there. So it focuses training on the more ambiguous or challenging examples where the learning signal is stronger. Plus, it aggregates losses at the token level, which we'll talk more about, to fight length bias. And it adds special reward shaping for overlong or truncated responses, trying to handle the variable output lengths in reasoning tasks better.
Okay, so DAPO is packing in a lot of specific tricks. It feels like a kitchen sink approach trying to solve multiple problems. But, as the paper's title asks, are all those tricks necessary, or are some potentially traps? This is where the detailed breakdown becomes really valuable, right? So after setting up these base algorithms, the researchers really went deep, dissecting the individual components. They looked at normalization, clipping, how loss is aggregated, filtering, all these little knobs and levers. So let's get into it. Which of these tricks actually proved valuable, and which maybe weren't so helpful, or were even traps in some cases? The paper focuses on 4 key areas: normalization, clipping, loss aggregation, and overlong filtering. Let's break these down one by one.
Okay, let's start with advantage normalization. This is really fundamental for stabilizing RL training. The core problem it solves is that reward or advantage signals can have wildly different scales or distributions. This can make gradients erratic, leading to unstable training. Maybe updates are too big or too small. By normalizing these values, we essentially rescale the feedback signal, making the gradients more manageable, preventing those wild updates. Think of it like setting a consistent volume on your feedback, no sudden shouts or whispers. This consistency allows for smoother, more efficient learning. It's pretty crucial.
It makes perfect sense. Consistent feedback is key. But this is where we hit that big contradiction you mentioned earlier, the whole batch level versus group level debate. So what did the paper find? What's the real difference? And critically, which one came out on top and when? This feels like a really important piece of the puzzle.
Absolutely. This is where a lot of confusion came from. And the key insight isn't that one is universally better. It's all about how your reward mechanism is set up and the kind of data you have. Let's clarify the difference again. Group level normalization calculates advantage relative to other responses for the same prompt. It fosters intra-context competition. Formula. A group K, RKU, or STD-RJ, for response K in a group. It really focuses on differences within that specific prompt's answers. Batch-level normalization computes this over the entire batch of samples, many different prompts and their responses together. It gives a more global view. Formula. A batchmo, ISE-SD across the whole batch.
Okay, so group is local competition, batch is global comparison.
Exactly. And the paper found their effectiveness is highly sensitive to the reward mechanism. When rewards were simple binary values, R, 0, 1, just correct or incorrect group level, consistently gave more stable training and better final results for the Qwen3 base models. In that setting, batch-level normalization often just collapsed. It was too sensitive to skewed rewards in the batch where a few outliers could mess everything up. And here's the twist, when they amplify the reward scale, say to R-high 1, giving more weight to incorrect answers, batch levels suddenly worked much better. It regained effectiveness and showed significant improvement. So it highlights that these aren't universally good or bad. Their utility depends heavily on the context specifically, your reward signal, and its distribution. It's not just which technique, but when and with what kind of reward.
Wow, that's a really surprising finding batch level collapsing and then coming back strong just by changing the reward scale. Makes me wonder about the parts of the normalization formula itself. The paper talks about sometimes removing the standard deviation term. Why would you do that?
Yeah, that's another specific tactic they investigated. The standard deviation term scales the advantages, right? But imagine you're working with an easy data set where most answers for a given prompt are either all correct or all incorrect. The rewards within that group are very similar. In that case, the standard deviation can become tiny, almost zero. And when you divide by a tiny number in the normalization, boom, you get huge, unstable gradient updates, like amplifying noise. The paper calls this similar to difficulty bias. The model gets overly influenced by these extreme amplified gradients from low variance groups. So they found that removing the standard deviation term, just doing ASTE, or ESK8, or AAO, AEE, AAM-BOR, is subtracting the mean without dividing by a set of, in these highly concentrated reward situations like easy data, significantly improves stability and effectiveness. It avoids those numerical explosions. For hard data sets where reward variance is naturally high, both approaches worked fine. So removing the standard deviation isn't a general rule, but a specific trick for low variance reward situations. Context matters again.
Okay, so given all these nuances, group versus batch, mean, keeping or removing the standard deviation, what's the practical takeaway? Is there a combination that emerged as generally more robust, a kind of best practice?
This is where they synthesize their findings into a really powerful hybrid approach. The research points to calculating the mean at the group level, keeping that local context sensitivity, but calculating the standard deviation at the batch level, using the global variance for more stable scaling. This hybrid approach provides much more robust reward shaping. The batch-level standard deviation gives a stronger, more generalized normalization effect, effectively scaling down gradients across the whole diverse batch, not just within one potentially uniform group. This helps prevent excessive policy updates, especially with sparse rewards, leading to more stable learning overall. It's a clever mix. Local sensitivity from the group mean, global stability from the batch standard deviation. It leverages the strengths of both, and empirically confirmed that batch-level elements can be very effective when used thoughtfully.
All right, moving on to clipping. We know it's there in PPO to stabilize things, but the paper suggests standard clipping can cause its own problems, especially for text generation. What's this entropy collapse issue, and why is it bad for LLMs?
Entropy collapse is a really critical problem. It's when the model's policy becomes too deterministic, too predictable. It loses diversity and its ability to explore different possibilities. Imagine an LLM that always picks the most obvious next word. It might sound coherent, but it won't generate novel ideas or find creative solutions. Traditional PPO kiting, by limiting how much the policy can change, can unintentionally suppress those low probability tokens. These are the less common words or phrases, but they might be exactly what's needed for an innovative step or a different line of reasoning. This creates a negative feedback loop: less diversity, less exploration, reinforcing higher probability patterns, even less diversity, and so on. The model gets stuck in a rut. For complex reasoning, where finding new solution paths is often key, this is a major roadblock. It limits the model's adaptability and problem-solving power.
Okay, so ClipHire is proposed as a trick to fight this. How does it work? How does it encourage that exploration we need?
ClipHire modifies the PPO objective by decoupling the clipping range. Instead of the symmetric one end-line epsilon, it uses one epsilon low and one plus epsilon high, crucially allowing epsilon high to be larger. By allowing a higher upper bound, it gives those potentially valuable low-probability tokens more room to improve. It expands the allowed range for policy updates when an action performs well, encouraging the model to sample more diversely and explore more. The idea is to allow bigger updates for underrepresented tokens if they prove useful, directly counteracting entropy collapse and fostering richer, more diverse generation.
Now, this next part really grabbed my attention. The paper found ClipHire's impact wasn't universal. It depended heavily on the model. Can you explain that? Does it work for all LLMs, or are some just better suited for it?
This is where the model's architecture and pre-training really come into play. The findings here are very clear. For base models, the raw, pre-trained ones without instruction tuning ClipHire actually had minimal effect, sometimes even hurting performance slightly. These models already have a low clipping rate, and their inherent ability to explore is somewhat limited anyway. Just raising the clip doesn't magically grant them exploration skills they don't possess. But for aligned models, those that have had instruction tuning or other alignment steps, making them better at following instructions and reasoning the story was completely different. For these models, raising the upper clipping bounds significantly slowed down entropy collapse and led to consistent performance improvements. These models already have better reasoning and a more diverse starting point. The higher clip helps them leverage that inherent capacity for exploration more effectively. It unlocks potential they already have.
So it's like giving an expert artisan more freedom makes them better, but giving a beginner too much freedom might just lead to mistakes. It really speaks to the model's initial state, doesn't it?
It absolutely does. It suggests clip higher acts more like an amplifier for existing exploration capacity. If a model starts strong and diverse, like aligned models, a higher clip lets it flourish. If it starts more rigid, like base models, a higher clip doesn't help much and might even destabilize it. It really underscores the need to consider the model's fundamental capabilities before applying these kinds of advanced techniques. It's not a one-size-fits-all solution.
And here's where it got really fascinating for me. They even looked at how clip higher affects their reasoning logic at the token level. What did they find about the actual language being generated? How does it change the way the model thinks?
Yeah, the linguistic analysis is quite insightful. They found that traditional clipping with a lower upper bound, like 0.20, tended to clip connective tokens more often in words like therefore, if, but, so, alternatively. These are precisely the words that introduce new reasoning steps, structure arguments, signal logical flow. By aggressively limiting changes to these tokens, traditional clipping might ensure stability, but it also unintentionally restricts the model's ability to generate diverse or complex argument structures. It makes the reasoning more predictable, maybe less nuanced. But when they raised the upper bound to, say, 0.28, the clipping shifted. It started clipping high-frequency functional tokens like is, the more often, and eased off on those crucial connective words. This subtle shift gives the model more freedom to explore different ways of connecting ideas, promoting diversity in its reasoning structures, while still keeping the basic sentence structure stable. It directly impacts the linguistic expression of logic.
That's incredible. It's not just about accuracy scores, it's about the actual texture of the model's reasoning.
Yeah.
You give specific examples. Which tokens get unclipped and allow these new paths?
Yes, figure 11 in the paper shows this really well. With the low clip, 0.20 tokens like therefore is, so, if, but, maybe, alternatively, wait, let all words that signal shifts in thought or logic were clipped more frequently. When they raised the clip to 0.28, the clipping frequency for these discourse-level connectives dropped significantly. The model had more freedom to use them. The clipping that remained then focused more on common function words, maintaining grammatical structure without hindering the creative flow of reasoning. It's like letting a writer use conjunctions and transition phrases more freely, trusting them to build sound arguments.
Okay, so if clip higher is good for aligned models, how high should we set that upper bound? Is there an optimal number or maybe a scaling law?
They looked into that hyperparameter too. And again, it depends on the model. For the smaller aligned model, Quinn34b, they did find a kind of scaling law. Performance generally improved as the upper bound increased, peaking around 0.32, which is higher than the often used 0.28. This suggests smaller aligned models benefit from more exploration room up to a point. But for the larger aligned model, Quinn38b, this clear scaling wasn't there. A value like modal 0.28 still performed very well, suggesting larger models might saturate earlier or have different sensitivities. So no single magic number. It's model size dependent, which makes sense, but it's great to have that empirical backing. All right, let's talk about loss aggregation. This determines how much influence each part of the model's output has on the training gradient. It's subtle, but important. Traditionally, sequence-level aggregation averages the loss across all tokens within a single response, and then averages those per-response losses across the batch. The problem, highlighted by previous work, is length bias. Longer responses, even if correct, have their influence diluted because the loss is averaged over more tokens. Each individual token in a long response contributes less to the final update. This can bias the model towards shorter answers because a short correct answer gives a stronger per token learning signal. It might learn to be brief even when a longer, more thorough answer is better.
That length bias sounds like a real issue, especially for complex tasks where the answer needs to be long. So how do they fix that? I guess this is where token-level aggregation comes in. What's the difference in calculation?
Exactly. Token-level aggregation aims to fix this. Instead of averaging per response, it sums the losses across all tokens from all samples in the entire batch, and then normalizes by the total number of tokens in that batch. This ensures that every single token contributes equally to the final loss calculation, regardless of how long the response it came from was. It's about giving every word, every step in the reasoning, its fair share of influence on learning, eliminating that bias against necessary verbosity.
That seems like a clear improvement, aiming for fairness across tokens. Does token-level loss always work better than sequence level, or are there nuances again?
Not universally, and this is another key finding reinforcing the theme of context dependency. For base models, the raw, unaligned ones' token level loss consistently led to better convergence, higher peak accuracy, and more robustness, especially on harder datasets. This makes sense, right? Base models are still learning the fundamentals, so making sure every token contributes equally helps them build that solid foundation. But for aligned models, the ones already tuned and good at generating coherent outputs, the advantage often disappeared. In fact, sequence-level aggregation frequently outperformed token-level for aligned models across many datasets. The reasoning might be that aligned models already have strong internal structures for generating high-quality, coherent responses. Token-level loss might actually disrupt this holistic structure, while sequence-level, by considering the whole response, helps preserve it.
So what helps the beginner model might hinder the more advanced one. Another example of needing to tailor the technique to the model's capabilities.
Okay, last of the four main techniques. Overlong filtering. When we train LLMs, we usually set a maximum output length, right? For practical reasons, managing compute. But for complex reasoning, especially early in training, the model might be on the right track but get cut off by this limit before finishing. This partially correct but truncated answer might get marked as wrong, 0 reward, which is misleading. It pollutes the training signal, teaching the model to avoid paths that might have actually worked if given more length. It hinders learning effectiveness.
And overlong filtering is the proposed trick for this. How does it stop that signal pollution?
It works by masking, or essentially ignoring, the reward signal from responses that exceed a certain length threshold. By deprioritizing these truncated, potentially noisy samples, it helps keep the training loss cleaner and prevents the model from learning the wrong lessons from being artificially cut off. It's basically trying to ensure the model learns most from complete thoughts, whether they end up being right or wrong, not from half-finished ones.
Does this filtering work the same regardless of where you set that length threshold? Is the cutoff point important?
Yes, the mask threshold, the maximum length before filtering kicks in, turned out to be crucial. When the threshold was relatively tight, like 8,000 tokens, 8K, overlong filtering showed significant benefits. Models learned to generate shorter, more accurate answers, seemingly becoming more concise and complete within that limit. But when they used a much longer threshold, like 20,000 tokens, 20K, the benefits mostly vanished. At that point, the filtering mainly caught genuinely bad outputs, repetitive loops, non-terminating gibberish rather than potentially valid reasoning that just got cut off. So its effectiveness depends heavily on setting the threshold that matches the realistic expected length of a good answer for the task.
Right, so it's about finding that sweet spot filtering noise,
Yeah.
but not accidentally suppressing genuinely long, valid reasoning.
Exactly. It suggests overlong filtering isn't a magic bullet for enabling super long-tail reasoning, but it can significantly improve accuracy and conciseness for tasks where answers should be reasonably bounded. It helps the model learn to be complete and concise rather than rambling. And one particularly interesting side effect was its impact on what they call no-stop repetition anomalies. This is when models, especially instruction-tuned ones in RL, get stuck repeating themselves and never generate the end-of-sequence token. They just can't stop. Overlong filtering significantly reduced these cases. It seems to help the model better distinguish between a properly finished thought and just getting cut off or stuck, allowing it to learn correct termination behavior and ignore those invalid repetitive loops.
That's super important for usability. You don't want a model just repeating the last phrase infinitely. It's like teaching it to put a period at the end of the sentence and be done. Okay, so after meticulously analyzing all these individual techniques, the good, the bad, the context dependent, the paper builds towards a really big reveal. A minimalist approach called Lite PPO that seriously challenges the idea that more complexity is always better.
This is where it gets really interesting, right?
Indeed. This is the synthesis, the aha moment that ties it all together and offers a potentially paradigm-shifting perspective. After all that dissection, they identified two specific techniques as being individually superior and broadly beneficial, especially for the non-aligned base models. These two were: one, advantage normalization, using that specific hybrid approach, group-level mean, batch-level standard deviation. This proved very robust for shaping rewards effectively. And two, token-level loss aggregation. This was particularly effective for base models, ensuring every token contributed fairly, which is critical when learning complex reasoning from scratch. So Lite PPO just combines these two specific techniques. That's it.
That feels bold when other algorithms like DPO are throwing in 5 or more components.
It is bold. The hypothesis was that the synergy of just these two core proven techniques would be powerful enough. So Lite PPO integrates just these two components into the vanilla PPO framework, and importantly, it does so without needing a critic, simplifying the architecture even further. The idea is maximum impact with minimum complexity, avoiding potential traps from less essential or context-sensitive components.
And the results. How did this minimalist Lite PPO actually perform against the more complex feature-packed algorithms like GRPO and DPO?
The results were really quite compelling, a strong validation of their approach. Lite PPO consistently outperformed both GRPO and ADAPO, especially on the base models they focused on. Remember, DAPO has 5 distinct techniques packed in. GRPO is also a sophisticated algorithm, yet Lite PPO, with just 2 core tricks, showed superior performance. Looking at their graphs, like Figure 16 comparing methods on Qwen 3.4b base and Qwen 3.8b base Lite PPO, consistently hits higher accuracy levels and maintains more stable learning curves. For instance, on the 4B model with easy data, Lite PPO gets over 40% accuracy and stays there, while DPO drops below 20% and GOPO is lower still. On the 8B model with hard data, Lite PPO again shows higher peat and sustained accuracy near 48%, clearly beating the others, which sometimes even collapsed after peaking. These aren't small differences. It's a significant improvement in both final performance and training stability.
That really is a huge finding. It's substantial improvement from a much simpler approach, especially avoiding those performance collapses. Why do you think Lite PPO manages this? What's the underlying reason for its success?
It really seems to stem from the targeted robustness of its chosen techniques and, critically, what it leaves out. That hybrid advantage normalization effectively handles tricky reward distributions. Token level loss optimizes learning efficiently for base models by giving equal weight to all reasoning steps. And crucially, Lite PPO omits things like overlong filtering, which the paper showed could actually be restrictive for base models trying to generate long, complex outputs. It also avoids decoupled clipping, which wasn't very effective for base models either. By selectively using only the tricks proven most impactful for base models and avoiding the traps of unnecessary complexity or techniques suited only for aligned models, Lite PPO achieves a kind of elegant efficiency. It leverages the core principles effectively without getting bogged down.
This paper does such a great job providing clarity, a real roadmap. But whenever we dive deep like this, I always wonder, what's just outside the frame? What questions does this research raise, even if it doesn't answer them directly? For example, Lite PPO wins on performance and simplicity. But what about computational cost? Are those 5 techniques in DAPO just way more expensive to run or tune? Does Lite PPO win on efficiency too?
That's a critical, practical question, and while the paper doesn't explicitly quantify it, it's highly likely. More components, like in DPO decoupled clipping, dynamic filtering, special reward shaping, almost certainly mean more computations per training step. More calculations, more memory needed, potentially more hyperparameters to tune, which takes time and resources. So yes, it's very probable that a simpler architecture like Lite PPO would inherently be more resource efficient. Faster training iterations, quicker experimentation. In industry, where training these huge models is incredibly expensive, that efficiency could be a massive, unspoken advantage, making Lite TPO not just better performing, but also more practical and sustainable to deploy.
Okay, another thing, generalizability. The paper focuses heavily on the Qwen 3 models and math reasoning. How confident can we be that these findings, especially Lite PPO's success, apply to other model families, Llama, Strahl, whatever comes next, or different tasks like creative writing or complex summarization?
That's a really important point, and the authors themselves acknowledge this limitation. They explicitly state that conclusions may vary across LLM families due to differences in pre-training and architecture. So while the findings are strong for Qwen 3 and math, we absolutely need more empirical validation to generalize universally. Different models might have different sensitivities. A model tuned for creativity might respond differently to clipping than one tuned for logic. The underlying principles, like the importance of context, matching techniques to model type, the power of normalization probably hold. But the specific recipe, the optimal combination of tricks, might definitely shift. It's a key area for future work.
And thinking about those model types, you mentioned how aligned models react differently. What about the reward function itself? The paper looks at reward scales, but does it give hints about designing a better reward function from the start, rather than just tweaking how we normalize whatever reward we have?
That's a great question, digging a level deeper. The paper focuses more on how normalization techniques cope with different reward signals, like binary versus scaled. It doesn't delve deeply into the art and science of crafting that initial reward function to be inherently better. And optimal reward design is absolutely paramount, right? A flawed reward signal will mislead the model no matter how well you normalize it later. The paper implicitly suggests this is important, but future work could definitely explore creating more robust reward signals up front. Maybe rewards that give partial credit, or are learned from preferences, or incorporate more nuanced error analysis rather than just simple pass-fail. Making the reward signal itself smarter could significantly reduce the burden on downstream techniques like normalization.
It makes sense. And one last practical thought. We saw that scaling law for clipping on small models and how loss aggregation depends on alignment. For teams deploying these models, how hard is it to actually tune these things dynamically? Switching between token and sequence loss, adjusting clip bounds based on the model, that sounds like a headache for deployment.
It's a significant engineering challenge, no doubt. Translating these nuanced research findings into automated, adaptive systems for production is non-trivial. It implies needing really robust validation pipelines to quickly figure out the best configuration for a given model and task, and maybe even adapt it over time. Manual tuning is slow and expensive. This is exactly why the paper calls for standardized frameworks and modular suites. The goal is to make it easier to swap components, experiment, and find the optimal setup without massive re-engineering each time. Bridging that gap between research insight and seamless adaptive deployment is a major ongoing effort in the field. And the researchers see this work as a foundation. Their future plans include continued monitoring, keeping tabs on new RL4 LLM techniques and evaluating them rigorously, unified frameworks, building out their role framework to make benchmarking and combining techniques easier, and streamlined algorithms. Continuing the search for minimalist, high-performance approaches like Lite PPO, focusing on efficiency, #tag outro.
Wow. Okay, what an incredible deep dive that was. We started in this kind of confusing mess of RL techniques for LLMs, and this paper really feels like it's given us a compass. The huge takeaway for me is that simplicity can genuinely outperform complexity. Lite PPO, with just those two carefully picked techniques, seriously questions the more is better mantra in RL4 LLM. And that insight about how things like clip higher literally shape the model's linguistic reasoning. That's just mind-blowing. It shows these aren't just abstract parameters. They directly affect how the AI thinks.
Absolutely. I think the core message is the critical importance of contextual adaptability. There's no single silver bullet, no best trick for everything. Effectiveness is so sensitive to the model's starting point, the reward setup, even the data difficulty. Understanding the mechanisms, the why behind these techniques, rather than just applying them blindly, is crucial. This kind of systematic work helps cut through the fragmentation and really does pave the way for more rigorous, efficient, and ultimately more powerful LLM development.
So for you, our listener, maybe something to think about. If this minimalist approach, focusing on just a couple of core impactful principles, can unlock such big gains in something as complex as LLMs, where else? Maybe in other areas of AI or even in our own work or learning, might we be over-engineering things? Where could we achieve more by focusing on fewer, truly fundamental principles, instead of just adding more layers of complexity? It's a powerful thought for innovation, I think. Thank you so much for joining us on this deep dive into RL for LLM reasoning. If this sparked more questions, or if you want to keep up with the absolute cutting edge of AI and ML research, please remember to visit neurolental.org and subscribe to our YouTube channel. Until next time, keep learning, keep questioning, and keep exploring.